Yes, perfect.
Okay, thank you. Then, yes, hello everyone. My name is Marcos Nieto. I work for Vicomtech. I have the pleasure to work with all these colleagues in this amazing project. And now that we have the OpenLABEL version 1.0.0 up and running, we are happy to explain it with these webinars and also with subsequent releases of the standard. I will try to summarize a little bit the aspects about data format in the next few minutes. So I will first say what do we understand as data format. I will then explain a little bit about why we chosen the JSON schema as the mechanism to materialize the format, and a little bit of examples of the JSON structure for different use cases, and also what the data format allows to build with the different data types that we have defined. So, quick introduction. What do we understand as annotation format? Well, it is the definition of the structure of the annotations, the data types involved, and the conventions that we have agreed in the standard so that anyone reading the annotations can unambiguously interpret the content or the meaning of the annotations. For that purpose, we definitely need an annotation file format, which is simply a representation of these annotation data in the defined format so that it can be stored as computer files. Once we have these definitions in place, we decided that JSON schema is a good mechanism to tackle both things, because on the one hand, we adopted JSON, the good, well-known JavaScript object notation format to host the annotations defined for OpenLABEL. But at the same time, we have the schema, which help us to objectively define not only the structure, but also the restrictions or conditions of the different content inside. Then let's talk a little bit about the schema itself. If you're familiar with JSON schema, in principle, a schema simply defines the terms of the labels that they will be hosted as key value pairs. Therefore, we have the terms of the labels as keys and the types of the values defined in the schema. It also defines the structure of the hierarchy, how things can be nested inside each other, and as well restrictions and conditions on the keys and values. That means that, for instance, we can define whether a particular term is required or optional, or maybe we can also define, thanks to the capabilities of JSON schema language, whether there are some options we can choose, for instance, within an enumeration of a number of types. In particular, the schema is used to validate JSON files. So imagine you have or you receive JSON content, maybe some files or maybe some payload, and you want to validate whether they are compliant with the OpenLABEL standard. Then you can use the OpenLABEL JSON schema, which will run through the JSON content and validate that it is compliant against the definition of the hierarchies, the types, and the restrictions. Also, the schema is quite good to produce formal documentation, and it has been very useful during the development of the documentation itself, because we populated the file with descriptions of every item, and this was automatically, well, thanks to some scripting, dumped into the document itself, so that when we modify or upgrade the schema, the documentation will be upgraded accordingly and automatically. That's a good thing for the, let's say, long-term development of OpenLABEL as a documentation and the schema. And last but not least, the schema, the JSON schema, can be parsed by programming languages in any object-oriented programming. So you can see that it's rather simple to have OpenLABEL parser in most modern languages such as JavaScript, Python, C++, Java, etc. All right. We have seen some examples through the morning that we have already seen some JSON snippets here and there. Let's take a quick look about the basics. Of course, all the details can be found in the documentation, so take a look there. But yes, in the next few minutes, I can explain that OpenLABEL has a very basic structure, hierarchy level. You can see it basic as a dictionary with key value pairs. And the most simpler OpenLABEL file will look like this. You have a root element called OpenLABEL, and then you have the schema version, which defines which schema and definitely which OpenLABEL version we are following in this file. At the root level, we can have these first level elements. These are objects mostly, which will be defining for description of physical entities, as we have seen in the examples in the previous presentation, such as objects, pedestrians, traffic signs, etc. But the schema already includes a good number of other type of elements, such as actions, events, contexts, and relations, which provides a powerful and flexibility to the capabilities of describing things that has happened in the scenes. There will be also frames and frame intervals, which define the temporal dimensions of the annotations, and a rest of other things such as streams, coordinate systems, resources, and ontologies, which help to link data all together. Last but not least, we also have the element tags, as explained by my colleagues, and also in next presentations, we will see that there is an entire branch of OpenLABEL devoted to labeling, let's say, tagging scenario files. Okay, what a simple object look like in OpenLABEL? Just like this. At the left, you can see that we have an element which encloses objects, and all objects have a unique identifier, which can be, as we can see at the left, an integer, maybe 0, or as we can see at the right, universal UID of 32 bytes. Inside the object, then we have mandatorily the name and the type of the object. In this case, a car, maybe a van. Having a name and a type follows the principles of OpenX ontology, because this way we can define that this is an instance with this name, maybe car1, of a type or class car, which is defined in an ontology. We will see how to do this in OpenLABEL as well. By adding the field ontologies, which also follow the key value approach, we can define as many ontologies as we wish. For instance, we can use the ontology defined for OpenLABEL, but you can also use your own. And then you can define that for object 0, for instance, you have a particular ontology UID where the type of the object is defined. So you can create your objects, label them, add their name and their type, and simply relate that in this resource, this ontology, the description of this class is can be found. Similarly, the tagging for scenario files is particularly equivalent in the sense that we also have in the metadata the schema version, but also the URI of the target file, because as you know, this JSON file will be containing the annotations of a particularly target file, maybe an open scenario file, right? In this case, for ontologies, we have a little bit more richness, because we can have these simple URI, for instance, from an ontology of yours, but also you can define a richer way of defining which ontologies and which subset of the ontologies are being used. More details will be explained by our colleagues later on. Equivalently to objects, we have tags, which also have unique identifiers, which can be integers, let's say numerical, or also UUID of 32 bytes. And inside as well, we can have the type, which is the class of the tag, and which where we can find the description of the class in which ontology. We can also see here the tag data, which is basically additional attributes or properties of the tag in this case. Coming back to objects for 1 second, we have seen how to create objects and how to name them and define which type they are related to. But we also want to provide geometrical information. So that's the way it's to include information inside the object data fields. For instance, in this example, we are defining bounding boxes, yes, in plural, because we can have an array of them. For instance, to define the head and the body of some pedestrians in images. As you can imagine, you can have here flexibility to add as many bounding boxes as you wish and any other geometrical types. As we will see at the end of the presentation, we can have lines, polylines, cuboids, etc. Each object data, for instance, the bounding boxes can have their own attributes because it's very useful sometimes to provide numerical, Boolean, textual attributes of the bounding boxes in this case, such as to define whether they are visible, interpolated, maybe to add some score value, etc. This is often the case in machine learning approaches. But you're probably wondering how to add the time dimension. Well, the answer is adding frames. So there is this mechanism that we have defined in OpenLABEL to have a list, a dictionary of frames, each of them tagged with a particular index that encloses all the information that is active in a particular frame. In the documentation, you can find how the different and complex setups have been managed because you can have multiple streams with different synchronization setups and time stamping that we have considered. For instance, you can imagine that we have a labeling tool, as in the example in the right image, and you are labeling a particular object, maybe a car, and you want to navigate through time, and then for each frame, you can add for instance, the one bounding box, or maybe several bounding boxes, maybe one for the license plate or whatever. Then you can add it as in the example. Inside frames, you can find which frame you are labeling, maybe frame number 0. Then you have objects, maybe this is object number 1, and then the bounding box. At the root level, we still have the objects themselves for the static information of the object, maybe the type, the name, and other attributes that might be non-dynamic, such as maybe the color, the brand, or any other thing. For those of you wondering what happens if you have multiple cameras, well, the answer is to have different streams. So in OpenLABEL, we can define as many streams as we wish. For instance, camera 1, 2, 3, 4, maybe a surround view system with 4 cameras or maybe more, or even different type of sensors, not only cameras, but also laser scanner, radar, etc. The idea is that you can add stream properties for each of these streams so that you can define the intrinsic values for cameras, for instance, or any other information about the stream itself. So far in the documentation, in this version, we have added a number of popular models for cameras, such as pinhole or fisheye, and more will be added in subsequent releases. And one particular or interesting aspect as well is the ability to project annotations from one domain to another. So imagine you have multiple cameras which are installed in a car. Then you probably want to have a coordinate system for the car itself, and then coordinate system for each of the cameras, and also maybe for the laser scanner, etc. So we can think about the situation in which the car itself is moving. Then we also have an additional coordinate system for the world. And all of these can be encoded within the OpenLABEL JSON files with the coordinate system entries. We can define as many coordinate systems as we wish and define a hierarchy of parent and child relationships between them and define what is the pose between them all in a Euclidean space. We can define this as 4x4 homogeneous matrices or other sort of representations such as Euler angles plus translation. In principle, when you have this included into your JSON file, that means that a reading or parsing application can read, for instance, bounding boxes in 3D space and project them into the images by using this type of transformation information. So let's take a quick look to the what data types have been defined so far. We have the generic data types that we have seen in the examples. So we can define numbers, text, vectors of numbers or other things, maybe vector of strings, booleans. But in general, we have created OpenLabel with the intention to be flexible and extensible so that we can extend any type of data type, such as number, with attributes and custom properties. So don't be afraid of adding your customized content here, so you can still use OpenLabel for your particularly complex data types. You have, in any case, actually a long list of defined data types. So we have tried to cover most of the most popular use cases, and with the ability of adding and nesting attributes inside each other, we are pretty confident that you can basically represent anything with this list of data types. So for the geometric types, we have bounding boxes, rotated bounding boxes, cuboids, but you can also add images themselves, matrices, binary content, polylines in 2D and 3D space, points, and more complex structures such as meshes, which encodes the ability to have 3D geometries. That's all. I know it's been pretty fast. There's a lot of more details in the documentation, and we hope that what we have done in terms of data format will be helpful for, let's say, the practical aspect of using OpenLabel. Thank you very much.
Thank you very much, Marcos.